Hello, welcome to lesson 10. In this lesson, we are going to continue looking at the determination of the focal length of a concave mirror, and then we shall also look at the determination of the focal length of a convex mirror, and lastly we shall look at some calculation examples. Let's begin by looking at the determination of the focal length of a concave mirror. We're going to look at method 3, that is using the no parallax method in locating V. Here's the setup. So here this is the setup. So what you're going to do is you are going to place a pin P1 which has been stuck on a cork. You're going to place an object pin P1 stuck on a cork, and you're going to place that object pin at a distance U away from a concave mirror which has been mounted on a mirror holder. Then after that, when you do that, you'll be in position to observe the image of that pin, an inverted image of that pin, through this concave mirror. So you'll be seeing that image, but you will not be in position to measure that image. So for you to measure the position of that image from the mirror, we shall need what we call a search pin. So we shall get a search pin. We shall get a search pin, that's another pin which has been stuck on a cork, and then we shall place it between the object pin and the concave mirror, and then we shall move that search pin. Between the object pin and the mirror, the concave mirror, until when the image of the pin P1, that is the object pin P1, coincides with the search pin P2. When that is achieved, we shall then measure the distance between the search pin and the concave mirror, and that distance we shall record it as V. Then the distance from the object pin up to the concave mirror, we shall record it as U. We need that distance U. And also the distance V, that is the distance from the search pin P2 up to the concave mirror. Then after that, we are going to repeat the procedure to obtain different values of U and V. We shall repeat the procedure to obtain different values of U and V, and then we shall tabulate our results, including values of U, V, and then U plus V. So we shall tabulate our results, including values of UV and U plus V. That means that on your table we shall have a column for U, a column for V, and a column for UV, and another column for U plus V. So we shall have 4 columns. Then after that, we shall plot a graph of UV against U plus V. And then we shall determine the slope of that graph, and that slope, we shall determine that slope S. After determining that slope S, we shall conclude that the focal length of this concave mirror is actually equal to that slope S. Let's look at the determination of the focal length of the convex mirror. We have also here a number of methods. Let's look at the first method, that is using a convex lens. So here we shall get our convex lens. We need a convex lens. Before we place the convex mirror, we shall place an object O in front of the convex lens, minus this mirror, minus the mirror. An object O is placed in front of the convex lens such that its real image is focused on a screen behind that lens. So we shall place our screen behind the lens, and then we shall focus a sharp image of that object O on the screen, and we shall record the distance between the screen and this lens, and that distance L I1 is going to be measured and recorded. Then after that we are going to place the convex mirror between the lens and the screen. We shall place this convex mirror between the lens and the screen, and Then we shall adjust that position of the mirror until when the image formed by that mirror coincides with the object by the no parallax method. Coincides with the object by the no parallax method. So on the object here, where the object is, we shall remember this object is usually an illuminated object which has also a screen besides it. So we shall move this until when we get a sharp image of that object formed where the object is. So they will be coinciding. When that is achieved, then we shall measure the distance LP. That's the distance between the convex lens and the convex mirror. Then after measuring that distance LP, we now need to get the focal length of this mirror. Now the focal length of this mirror is actually going to be got by getting the distance PI1, because this distance PI1 is actually the radius of curvature. The radius of curvature. So for us to get that distance PI1 is going to be LI1 minus LP, which is going to be twice of the focal length F. And therefore, if you want to get F, we shall have our F as LI1, this is going to be I subscript 1, minus LP divided by 2. So this is how we shall be in position. Remember, we have measured LI1 and LP. So we shall get the focal length of that mirror using this formula. Now let us note that how do we get that formula? We need to remember that when this ray is to go back along the same path so that the image is formed beside the object, so that the image I2 is formed beside the object, it means that the ray of light is going to be reflected along the same path. And if it is reflected along the same path, then it must be meeting this surface normally. So it implies that that light will be appearing to be coming from the center of curvature. So the distance PI1 is going to be the radius of curvature. And the radius of curvature is equal to twice F. So that PI1 is actually the radius of curvature. And so we shall have to divide that distance by 2 to get the focal length. Yeah, so that's the note here. Let's look at some examples. An object O is placed 40 centimeters in front of a convex mirror, a convex lens of focal length 15 centimeters, forming an image on the screen. A convex mirror situated 4 centimeters from the lens in the region between the lens and the screen forms the final image besides object O. Draw a ray diagram to show how the final image is formed, and then determine the focal length of the convex mirror. Now this is just similar to the experiment. The setup is just similar to the experiment. So the ray diagram is just going to be similar to that we have looked at in the experiment. So this is how it is. So the object is 40 centimeters in front of the convex lens. So this is 40. And then the focal length of that convex lens is 15. So we can use the 40 and the 15 to get the image distance, that's the distance LI1. So using the formula 1 over F is equal to 1 over U plus 1 over V, that is the lens formula. Remember, the lens formula is similar to the mirror formula. Of course, we shall look at lenses in the second part of optics. So this is the lens formula. So when we substitute for F and U, we can get the V. And so we shall make our V the subject and get our V as 24 centimeters. That means that the distance LI1 is going to be 24 centimeters. So if I want to get the distance PI1 is going to be 24 minus the distance LP, which is actually 4 centimeters. And so we shall get 24 minus 4, which will give us 20 centimeters. And therefore, R is equal to 2F. And so we shall have to f is equal to 20 centimeters, and then f is going to be 10 centimeters. But we need to recall that the center of curvature for a convex mirror is virtual, so f is going to be negative 10 centimeters. Let's look at the second method here, using a plane mirror and a no parallax method. So here we shall have the final setup, but before we achieve this setup, we are going to have an object O placed in front of a plane mirror M2. Sorry, a convex mirror M2, in front of a convex mirror M2, and it will be forming an image, a virtual image I, behind that convex mirror. So that image I is going to be seen. So we need to locate that image position. Remember, this image position, it is a virtual image, so you cannot actually measure that distance from the image up to the mirror. So what we are going to do is we are going to get a plane mirror and place it halfway the aperture. Halfway the aperture is the total diameter of that mirror. So we shall get it, place this plane mirror halfway the aperture of that mirror, halfway the aperture of that mirror, of the convex mirror. And then when we place it there, we are going to adjust that position. We shall adjust that position such that the image of this object O formed by this plane mirror, that image I prime, coincides with the image I of this object O formed by the convex mirror. This convex mirror forms an image, and this plane mirror also forms an image. So we shall adjust to that those two images are coinciding by the no parallax method. When we have achieved that, we shall then measure the distance. After achieving that, that's what I've been talking about. After achieving that, we shall measure the distance x and y. That distance x, that is the distance from the object to the plane mirror, and the distance from the plane mirror to the convex mirror. X and y will be measured. And then, after that, we shall use the formula, because now we are looking at this, we're going to use the mirror formula to get the f, the focal length of this mirror. Remember, the u is going to be x plus y, and the v is going to be this distance pi, which is actually the distance x plus minus this distance y. Remember, if this is x for a plane mirror, even the image distance is also going to be x. So that's how we see this one is also x. So this, if I want the distance pi, is going to be this x minus this y. But it's going to be virtual, so it's going to be negative. So we shall use the formula 1 over f is equal to 1 over u plus 1 over v, where u is equal to x plus y and v is equal to negative x minus y. Now let us make a note. So you need to note that when they are coinciding, when the two images are coinciding, that is I and I prime, when they are coinciding, then the distance between pi is equal to that distance between pi prime. So those distances will be equal. Pi and pi prime will be equal. And also we need to know that when we substitute for u equal to x plus y and v is equal to negative x minus y in the mirror formula, we shall get our f as y squared minus x squared divided by 2y. So when we substitute this and this here, and make f the subject, we shall have our f using this formula. So if you have x and y, you can just use this formula to get f. Let's look at some examples here. A plane mirror is placed 10 centimeters in front of a convex mirror so that it covers half of the mirror surface. A pin 25 centimeters in front of a plane mirror gives an image which coincides with that of the pin in the convex mirror. Find the focal length of the convex mirror. Find the focal length of the convex mirror. So here, when you look at this question, it is just similar to the experiment. So we are going to have the same setup, and it is going to be looking like this. So you can see that I've said the plane mirror is 10 centimeters in front of the convex mirror. So the distance from the plane mirror up to the convex mirror is 10 centimeters. A pin 25 centimeters in front of the plane mirror. So this pin is 25 centimeters from the plane mirror. So this is 25, x is 25. So u is going to be 25 plus 10, which gives you 35. And so we need v. So if this is 25, then this x is also 25. So if I want to get this distance, which is actually the negative v here, is going to be 25 minus 10. Negative of 25, negative of brackets 25 minus 10. And then we shall use the mirror formula. And then where u is x plus y and v is negative x minus y. When you substitute, for u is going to be 25, and then v is going to be negative of 15. So we shall have 1 over f is equal to 1 over 35 minus 1 over 15. And therefore f is going to be, got from this cross multiply, get your f as 525, divided by negative 25, negative 20, and therefore f is going to be negative 26.25 centimeters. Let us also look at this example here. A plane mirror is placed 10 centimeters in front of a convex mirror so that it covers about half of the mirror surface. A pin 20 centimeters in front of the plane mirror gives an image in it which coincides with that of the pin in the convex mirror. Find the focal length of the convex mirror. So when you look at this question, it's just similar to the question you have been looking at. The only difference here is the values. So we have the plane mirror is 10 centimeters in front of the convex mirror. So this is 10 centimeters. And then the pin is 20 centimeters in front of the plane mirror. The distance here is 20 centimeters. So u is going to be 20 plus 10, which is 30. And v is going to be, remember, if this is 20, then the distance from the plane mirror up to the image is also 20. So that is also 20. So if I want to get the v, it's going to be 20 minus 10, which gives us negative 10. And therefore, we shall use the formula. So we are saying use 30, v is negative 10. And since the image is virtual, it is a virtual image for the convex mirror. Using the formula, we shall get 1 over f is equal to 1 over u plus 1 over v, making v the subject. So making f the subject, shall have vu divided by u minus v. Then we substitute for v with negative 10 and u with 30. And then here also 30 and then negative 10, which will give us negative 15. Therefore, the focal length of that convex mirror is going to be negative 15 centimeters. So we still have other 12 lessons to cover in order to finish the first part of optics. So in those 12 lessons, shall be looking at refraction. If you're interested in those other lessons, please, you're going to be contacting me through this email, opacmark@gmail.com. It will be at an affordable cost. Yeah, thank you for your attention. Thank you for subscribing to my channel. I wish you the very best.